Welcome back, students, to our Chapter 11 video notes. We're going to pick up where we left off with changes of state. So some of this might initially be some review, so let's go ahead and just remind ourselves of a couple of the phase transitions that we already know about. So let's start between solid and liquid, and then we'll go to gas. So if you're taking a solid, like an ice cube, and letting it sit on the counter to turn into a liquid, we call that melting. In chemistry world, this can also be called fusion. If we go the other way and we go from a liquid to a gas, we call that freezing. Then once we're at a liquid, if that liquid turns into a gas, we call that evaporation, which is going to be hard to write on an angle. So I'm going to do this in a interesting fashion. I'm going to make that arrow thicker and then call this evaporation. In chemistry world, sometimes we call this vaporization. If we're going the other direction from gas to liquid, we are going to call that condensation. So most of these terms I expect that you probably already knew. The ones that you might not know are the less common ones. Believe it or not, a solid can turn directly into a gas, and you might have seen this with something called dry ice, which is solid carbon dioxide that's turning directly into a gas. That process is called sublimation. We use sublimation in organic chemistry lab, for example. When we want to purify a compound, we can use sublimation if the compound we're trying to purify can sublimate. Then what we can do is warm that compound. It turns directly into a gas. We give that compound a cold surface to then go through deposition on, right? And deposition is the opposite of sublimation. And then we collect that pure compound. In real life, other than dry ice, where you have seen sublimation would be in Vicks Vapor Rub. So in Vicks Vapor Rub, there's camphor, and camphor is a solid. And then when you rub it on yourself, it turns directly into a gas and then soothes you when you're not feeling your best. So let's look at some of these changes of state and how they're going to apply to the stuff we're going to discuss. So let's move into what molecules are doing when they change state. So let's pretend we're talking about liquid molecules. So this graph here is showing there we go, the fraction of the molecules that have a given kinetic energy, and then the x-axis is I guess the amount of kinetic energy increasing, right, going this direction. So this shaded in part here, those are the molecules that are moving fast enough in order for those liquid molecules to escape from the liquid and move into a gas. So what I envision when we're discussing this is maybe we have like a dish of water. And so, oh, that looks awful. Let's fix that. So on our dish of water, right, we've got the surface of the water, and that water surface is just made up of water molecules, right? It's just a bunch of water molecules sitting at the surface. And then there's water molecules in, let's call it the bulk. Such a weird way to say it, but It's what we say. So you got water molecules at the surface, and then you got water molecules in the bulk of the water. And so you can kind of think of the water molecules at the surface as, oh goodness, I didn't mean to do that. So the water molecules there at the surface are kind of like if you've ever played Red Rover. If you've played Red Rover, you know a whole bunch of people are standing in a line and they're holding hands. And then a whole bunch of other people run toward that line and they try and bust through and break through the line of folks who are holding hands. So how does that relate to phase changes? So these molecules in the water, they're always moving. So here I'll be like a little comic book, right? And those are my little like, I'm moving lines. So those water molecules are always moving, and some of those water molecules are moving fast enough to go ahead and Red Rover through the surface. And so they're moving fast enough to break through the surface of the water and break through the bulk and come over here and become gas molecules. And so when they break through that bulk, they're really close to molecules, like physically, right? And then they're also attracted to each other. And so really the molecules have to have enough kinetic energy to overcome those intermolecular forces that attract molecules to one another. And so that's what is going on when something evaporates. You have to have water molecules that can break through that surface. And so when those fast-moving water molecules leave, it decreases the average kinetic energy. And that makes sense, right? Because if we think about it in like a normal real life example, imagine that you're in a class and you have calculated the average score in the class and it's 70%. Well, pretend then all the A students in your class drop. Well, if all the A students in your class drop, the average in the class goes from a 70 to a 60. And so that's what's happening here. We're losing all of our A students, our fast-moving molecules, and so our average ends up decreasing. And because kinetic energy is proportional to temperature, the temperature of that mass of molecules also will decrease, at least slightly. And so let's talk about what evaporation depends upon. Evaporation depends upon surface area. If you have a larger surface area, then you have more opportunities for the water molecules to break through from the bulk out into a gas. So that's imagine like a little shallow dish, and here's my cup. Right here, we've got a whole bunch of molecules that can break through the surface. Because the surface has such a great area, there's a lot more opportunity. And so larger surface area, faster evaporation. If we look at what's next, temperature. Well, if the temperature increases, then the amount of molecules with this larger kinetic energy also increases. So you're going to see faster evaporation. If your molecules are weakly attracted to one another, oops, sorry, I said weakly, and I just circled the strong intermolecular attractions. So if your molecules are strongly attracted to one another, that means they really have to break those intermolecular forces, those strong intermolecular forces, in order to turn into a gas. But if the molecules are weakly attracted to each other, it doesn't take much energy at all for them to move away from their friends and turn into a gas. And so you'll see more evaporation in that instance. So let's talk about what's going to evaporate faster. Water in a pie plate or water in a small cup? So what do you think? What does surface area do? So we're looking at faster. You should say the one with the larger surface area. Pie plates tend to be 9 inches in diameter. Small cups, definitely not 9 inches. Okay, so next one, water that's polar or hexane that's nonpolar. So which one evaporates faster? Well, If water is polar, polar molecules have stronger intermolecular forces than nonpolar molecules. So, stronger intermolecular forces ends up meaning that it's more difficult for that to evaporate. And so hexane, the nonpolar, is going to evaporate faster. Okay, how about water in a cold room versus water in a warm room? Well, temperature is proportional to the kinetic energy. And so water in a cold room has molecules that are moving slower, and in comparison to water that is in a warm room. And so if we have water that's warm, the molecules move fast and can escape the surface more easily. And so that leads us to this amazing question. Why does water evaporating from your skin cool you down? Okay, I'm going to leave a cliffhanger here and we can talk about that one in class. I'm going to let you think about it for a day. So then we've talked about evaporation. Let's talk about condensation. Evaporation and condensation are opposite one another. So evaporation, as you know, is liquid turning into a gas. So condensation is the other direction. Let's look at this weird picture. And I say it's a weird picture because where in real life would you have taken a plate of water and put it in a glass box? Like, that's just silly. But of course chemists do these things, right? Because these are, I guess this is like the beginning scenario. Uh-oh, you're going to find out I don't know how to spell beginning. Begin. I feel like there's another N. Oh, darn. Well, as usual, you'll tell me in class. And this is the end situation. So imagine you put this pie plate in water and have water in it, and then you put a glass box around it. And imagine that glass box is a pretty secure one. It's not letting out any gas. So what you're seeing here is that the molecules of the liquid are coming out and they're evaporating and turning into a gas. And notice how we're getting more evaporation than we are the other direction here, condensation. And so at a certain point, we end up getting what's called an equilibrium. And in this case, we're getting something called a dynamic equilibrium. So that word dynamic means that we're talking about an equilibrium that's with respect to phase changes. And so let's talk about what an equilibrium is. In this case, the dynamic equilibrium is that the rate that you're seeing for evaporation is the same rate that you're seeing for condensation. So the molecules are evaporating and condensing at the same rate. So if you were to take a snapshot in time, what you would see is no net change, right? And net means overall. And so really molecules are always moving. And so even though you're seeing no net change, that doesn't mean that evaporation and condensation has ceased. It just means that they're happening at equal rates. And so you don't see a change any longer. And so let's talk about these gaseous molecules that are above that liquid, because those gaseous molecules are something that we can easily forget about. And those gaseous molecules, they create a pressure, and that pressure is called vapor pressure, right? So here's the definition right here. When a liquid evaporates, the vapor molecules exert a pressure. And you know this, but you often forget it. And so let's talk about how you know this. You know this because in real life, in the summertime, when it's humid out, you walk outside and you just encounter this wall of heat and you're like, oh man, gosh, is it humid? Well, humidity is just a measure of how many vapor molecules are in the air. And so during the winter, you have the opposite problem, right? In your house, you're like, oh my gosh, my nose is dry. I need my humidifier on because it looks more like this situation, right? Where there's less vapor molecules in the air. And so we need that water vapor in the air, to make us feel comfortable. And so this vapor pressure is something that is absolutely measurable. And so when we start thinking about vapor pressure, that vapor pressure depends on a couple of things. Obviously, it depends upon the temperature of the liquid, because the higher the temperature, the more evaporation you see. The more evaporation you see, the more gas molecules you have, and those gas molecules are what are exerting that pressure. And then, of course, the more evaporation you have, the same idea, the more gas molecules you have, those gas molecules exert a pressure. The intermolecular attractions also have an effect, because the intermolecular attractions are also related to evaporation. So if you have a strong intermolecular attractions, then you're going to have less vapor molecules, which means a lower vapor pressure. So let's summarize those two most important points here. As temperature increases, we're expecting to see an increase. Oh goodness. An increase in vapor pressure. As intermolecular interactions increase, we're going to see a decrease in vapor pressure. So let's answer these two questions. What has the higher vapor pressure? Water at 40 degrees or water at 90 degrees? So let's think about how temperature affects vapor pressure. We just said that if temperature is increasing, we have more gas molecules. The more gas molecules you have, the more molecules there are to exert a pressure. So absolutely, you are expecting a higher vapor pressure at a higher temperature. Okay, now let's talk about hexane versus nonane. In order to answer this, you need a little bit more information. You need to know that hexane is 6 carbons long and nonane is 9 carbons. So one thing that we didn't explicitly discuss in our intermolecular attraction section is that in addition to intermolecular forces affecting the attractions between molecules, the other thing is when we're talking really a lot when we talk about London dispersion forces, size matters. And so what I mean by that is, imagine hexane, the 6 carbon one, is like a 10-pound baby, and nonane is your 2-year-old baby. Which one is going to be easier for you to lift up? The small baby or the big baby? And so obviously something that's 10 pounds, whether it's a baby or a weight or whatever, is going to be much easier to lift than something that's 25 pounds. And so your molecules are going to be like that too, where the smaller molecule is going to have weaker attractions. Weaker attractions means that you're going to have a higher vapor pressure, because those weaker attractions result in how do I say this? Something that more easily evaporates, and thus you have more gas molecules. More gas molecules, more vapor. So this diagram over here is just illustrating that in addition to liquid and gaseous vapor pressure systems, you can also have a solid gas vapor pressure system. Like if this was dry ice, which is solid carbon dioxide, and then these would be, your gaseous molecules of carbon dioxide. So you can have, vapor pressure in both systems. And so let's look at what is next. Oh, what I just said is in words right here. Okay, so I don't need to repeat this because I just said that out loud. Let's go ahead and look at boiling point. Boiling point is a personal favorite of mine, and I know you probably think that sounds ridiculous, but as you well know, I love organic chemistry, and organic chemistry is has like a whole section on intermolecular forces and how they relate to boiling point. So that's why I love this one so much. So let's start by defining boiling point. Boiling point is when the atmospheric pressure equals the vapor pressure above the liquid. And so what ends up happening is boiling point then is affected by the pressure of the atmosphere. And so what we need to do here is draw a little diagram. So let's pretend we have a mountain. And here's you at the bottom of the mountain. And then here's you at the top of the mountain. And so at the top of the mountain, up here, the air is thin. So what does thin mean? Does thin mean a lower pressure or a higher pressure? So hopefully you said at the top of the mountain, pressure is low, right? And that pressure I'm referring to is the atmospheric pressure. So then down at the bottom of the mountain, we have a higher pressure. Especially if you're below sea level, right? Sea level has a pressure of about 1 atmosphere. Below sea level is going to be a little bit greater than that. Okay, so then let's think about you on the mountain again. Pretend you are on the mountain and you need to cook some spaghetti. Or maybe you are somebody who utilizes box cake mix and you need to bake a cake. And if you've ever utilized box cake mix and really read the box, it says something about, accounting for high altitude. And they have you bake it longer, or maybe they have you bake it at a higher temperature or something like that. And so when you start, boiling water to make pasta or whatever you're going to make, what you're going to find is that when you're up here where the air is thin and the pressure is low, the boiling point is also lower. So it decreases. So maybe instead of 100 degrees Celsius, which is the boiling point of water at 1 atmosphere, maybe you're at the top of the mountain, your boiling point is 95 degrees Celsius. And then as pressure increases, the boiling point increases. This can be really counterintuitive if you're not imagining yourself on a mountain. And so obviously as chemists, when we want to communicate with one another, it's really much more effective if we all measure boiling point at the same pressure so that pressure doesn't become a factor. And so remember that 760 torr is the same thing as 1 atmosphere. And this is called the normal boiling point. So when you hear somebody talk about the normal boiling point, that means they've taken the boiling point or measured the boiling point of a liquid at 1 atmosphere. So let's talk a little bit about how boiling point and intermolecular forces are related to one another. So as intermolecular forces increase, the boiling point also increases, which makes the contrary true, right? As the intermolecular force decreases, the boiling point decreases. So let's think about why. So when we talk about why, remember that something like water, a relatively small molecule, has the ability to hydrogen bond. So water is going to have this attraction between molecules because the oxygen has a partial negative, this hydrogen has a partial positive, right? And this right here that I just highlighted, that's your hydrogen bond, right? That attraction between the partial negative on one molecule and the partial positive on a neighboring molecule. So if you have strong intermolecular attractions, that's like having a strong magnet. And if you have a strong magnet, you can put a heck of a lot of energy to pull that magnet away from another magnet. So strong intermolecular attractions take a lot of energy to break. Because remember, the whole idea behind boiling was a molecule in the bulk breaking through the red rover surface and turning into a gas. In order to break through that red rover surface, it has to break through the attractions between itself and neighboring molecules. So if those attractions are really strong, it's going to take a heck of a lot of energy to break those attractions. So they take a lot of energy to break, and that results in a higher boiling point. And when you get to organic chemistry, we'll expand upon this. We'll have a great, like 5-sentence long answer, but this is perfectly fine for General Chemistry 1. So let's look at a little graph as we end this video. So as we finish up this video, let's look at this last question here. It's saying you got the pressure on the top of Mount McKinley is 330 torr. You're on the mountain. Oh, and oh my goodness, you have frostbite. Thank goodness you are climbing with a doctor who has a knife so that he can amputate you. Assuming the doctor is male. You know, the doctor could very well have been female. So the doctor is insistent that they need to sterilize that equipment with water at 100 degrees Celsius. And so let's look at our graph and see if we can get the boiling water on Mount McKinley to be 100 degrees Celsius. So let's sneak over to the y-axis and find 330-ish. So maybe it's about there. We come over, we hit water. That's not a very straight line, but who cares? And holy moly, would you look at that. That is nowhere near 100 degrees Celsius. Even with my pen not behaving, it's still like, what, 78 degrees Celsius? So no way. Water boils at a much lower temperature. On the top of Mount McKinley. I hope you enjoyed my silly example. Okay. Well, that's probably enough for one video, so why don't we go ahead and stop there. We'll pick up in the next one. So, hope you're enjoying chemistry, and Katoni signing out.